Okay, so now we're recording. Okay, so to motivate free energy, I want to talk about a specific phase transformation in tin, right? So low temperature phase in tin is actually a diamond cubic semiconductor tin with covalent bonds, right? You see that tin actually makes a tetrahedron bonded with four other um, tin atoms. And at higher temperatures, it becomes a metallic phase, which is unusual because it has a body-centered tetragonal unit cell, which makes plasticity and deformation in tin an interesting aspect. Anyway, the transformation temperature isn't too cold, right? 286 Kelvin. This is about 55 or so, 53 degrees Fahrenheit. And this gets the name, this transformation is called tin pest. Let me just pop up a quick video, right? And here's a block of tin. Here's the phase transformation. This, in case you haven't noticed, this is time-lapse, this transformation. The kinetics of this transformation are not at all fast. This is probably many hours compressed down into this this 30 seconds, but we go from a nice shiny metal to this gray semiconductor stuff. And of course, there's this apocryphal story that there's no real evidence for, but makes for a fun story anyway, is that, you know, the French army under Napoleon had tin buttons on their uniform, and then they invaded Russia during the middle of winter, and there was a phase transformation, and the buttons got brittle and fell off the uniform, and one of the reasons why Napoleon lost was because his soldiers couldn't hold up their pants. In reality, I think it was dysentery, but a good story nonetheless. Okay, so if we have an isothermal phase transformation like this, right? So if we hold this at some temperature near to slightly less than 286, right? Or this tin transformation is going to occur reversibly at 286 and irreversibly at any other temperature. So let's pretend we're just a tiny delta T, tiny dt below 286, so we have a tiny little bit of driving force to actually make this happen. Right, so if we assume constant pressure and a reversible process, so we have constant temperature, constant pressure, right? From our discussion of enthalpy, we know we can take the differential and we get this du plus pdv plus vdp. We know that the change in pressure is 0. We can substitute our first law, right? And essentially we have that the change in entropy is going to be our change in enthalpy divided by the temperature. So if we integrate this out at a constant temperature, right, we get a finite form, so we get the enthalpy change of the transformation, right? This delta HT, right? I'm going through this quickly because this really should just be a review. We can use this then to calculate the entropy change, and we get 7.3 joules per mole Kelvin, right? And if we multiply this by the temperature, right, we have something on the order of the we have the enthalpy of the phase transformation, right? But anyway, if we are holding this if we're at a constant temperature and we're in atmosphere, right? So the change in volume associated with this change is not going to change the pressure of the surroundings, right, we essentially get that if we go through the same analysis for the surroundings, we're going to get a negative, the same entropy change but negative, and we then see that the change in entropy for the system and the surroundings for a reversible change is 0, right? And of course, we know this intuitively because entropy is a measure of direction, right? If we have a increasing entropy change, we know we're going to be going in a spontaneous direction, right? A negative entropy change means we're of the system and the surrounding means that we're not going to happen, and that if the entropy balance between the system and the surroundings is exactly 0, it means it's going to be a reversible, completely reversible process, right? So that's a great bookmarking and accounting system, but it's often not very convenient to calculate our entropy change for both the system and the surroundings, right? It would be much, much, much more convenient if we had some function that only depended on the system and we could ignore the process, ignore the surroundings to determine if a process is going to be spontaneous, right? And luckily we do have such a function, and it's called the free energy. Right? And we can essentially consider a spontaneous process according to our second law, right? So if our change of entropy of our system plus the change of entropy of our surroundings is going to be greater than 0, and then we consider that sometimes if a process is reversible, the process itself is irreversible, meaning that we're doing our tin phase transformation at a temperature less than the equilibrium temperature, we can still transfer heat to the surroundings in a reversible manner, right? And it's not too hard to imagine because the atmosphere essentially is a constant pressure environment and we have a very small sort of undercooling, we can transfer things back and forth, right? And if we're under isobaric or constant pressure conditions, we know that our dq has to equal our little d enthalpy. And so we can plug that in. So essentially we have a reversible to the system. Oops. This should be, shoot, I looked at this like 1,000 times the other day. This should be force system, right? Meaning, so we're taking from the surrounding to the system, but then the change in the system is irreversible, just as the text says up here. And so what we essentially come up with is this dH minus TdS for the system has to be less than 0, right? And this is just the definition of our Gibbs free energy, right? The enthalpy change minus the temperature times the entropy change of our system has to be less than 0 for a spontaneous process. And for a reversible process, this has to be 0. And for a process that cannot proceed, this is going to be greater than 0, right? So the Gibbs free energy does what we want it to do. It tells us if a process is going to occur spontaneously without the need to consider our surroundings, right? Which is really a remarkable achievement, right? Of course, we can go through a very similar analysis for a constant volume process, rather than a constant pressure process. And this would be really important if we were doing chemical engineering. And we can define a Helmholtz free energy, right? Helmholtz free energy is really important in solid mechanics, where we're applying stress, when we're doing deformation processing of our material, when we're squishing it and we're applying large stresses and strains. Obviously we don't have constant pressure, right? Because putting a force on our material is going to change the pressure. But it turns out that plastic deformation conserves volume, right? So when we talk about, if we talk about solid mechanics, Helmholtz free energy is the relevant term. And what about processes that are neither isobaric nor isovolume? Well, there isn't a simple free energy function, right? We have to break things up, right? But for the most part, thinking about these two cases gets us 99% of the way there. Okay, so equilibrium. All right, now we're getting into the meat, right? So pretend we have a phase transformation. We have two arrangements of atoms, right? And if we know that we're going to try and minimize our Gibbs free energy, because if we're at equilibrium, our local change in Gibbs free energy has to be equal to 0. And if we're in some kind of energetic configuration where we are, some kind of atomic configuration where we can lower our entropy, so say we're here on this ordinate axis, we're going to tend to move in a direction that's going to lower our free energy, right? So if we have this parameterization of arrangement of atoms, if these are the possible configurations of our system, we're either going to be at this minima or this minima, right? So A here is the global minima of free energy, right? So for this configuration, I mean, this temperature and pressure, this is where our system really, really wants to go, right? But we could also be over here. We have a metastable equilibrium, right? Meaning that I have to raise the Gibbs free energy of my local configuration to get it over this hump down here, right? And this is what we're going to refer to as a activation barrier, right? So if we're talking about a temperature-induced phase transformation, what is our driving force, right? What is our source of energy? We have lots of thermal fluctuations going on. Our atoms, our molecules are constantly vibrating and jiggling. So we have local rearrangements that happen all the time due to these thermal fluctuations, right? And most of the time, the fluctuations are going to bounce us around this local state, right? But every so often, we might get a configuration that brings us up to here, right? And if we make it up to here, we've got a 50-50 chance of going down or going over, right? And so we can nucleate a small region that will get us over this transition hump and allow us to roll downhill to the actual equilibrium, right? And how difficult this transition is depends completely on how big this hump is, right? And it probably shouldn't be a surprise that the height of this hump, as we'll see when we talk about nucleation, is directly related to the time that this transformation takes, right? If this hump is very low, nucleation in this system won't be hard. If this hump is very high, nucleation will be very difficult. But that's sort of topic to get into in real detail at another time, okay? at the if we have multiple phases, multiple atomic configurations, the highest stability, the phase that has the highest stability, is going to be one that has the best compromise between enthalpy and entropy, right? At low temperatures, solid phases are more stable than liquid and vapor phases because they have the strongest atomic bonding, right? They have the lowest internal energy, the enthalpy. But as we raise the temperature, now this entropy times the temperature term can begin to dominate. And phases that have higher enthalpy, but that high enthalpy is balanced by a high entropy. And it allows phases with more freedom of atomic movement, liquids and gases, to become thermodynamically stable. Okay. Pressure changes, if we consider pressure changes, our phases with small volumes are going to be favored by high pressures.
Just to interject, we have a question in the chat. Where does water, how does water relate with that previous point?
So water is basically the same, right? Water has a higher enthalpy than ice, right? And while water is unusual in lots of aspects, it's not unusual in this, right? Because the liquid phase has a greater entropy, right? Than the solid phase, but solid ice has a much lower enthalpy, right? So what essentially happens is that this temperature, once this gets high enough and can boost this TS term, now the now it can melt. Okay. Waterfall with this ice increases volume. This is where ice and water is a little weird, in that the slope is backwards for the pressure phase diagram. And we will talk about that sort of in the future, right? Water is weird for lots of reasons because the crystal is made primarily of hydrogen bonds rather than covalent or ionic bonds or metallic bonds that we have. So water is weird with respect to the volume phases, but it's only the most common allotrope of ice, the one that we get to by freezing things in our freezer or in the atmosphere, right? The phase diagram, the pressure temperature phase diagram for water has many different crystal structures that are possible for ice, and not all of them have a larger volume than liquid water, right? So yeah, water is unusual, but we'll talk about it more. Okay, so thermo doesn't answer the question for us, how fast does a phase transformation occur, right? Metastable states can be very short-lived, or they can exist almost indefinitely, right? Diamond at room temperature and pressure is a metastable phase, right? But we're not worried about our jewelry turning into graphite. Heat it up, and it sure as heck will, right? And as I said before, the height of that free energy hump between the metastable and stable states is going to be strongly related to the kinetics, right? So this kinetics obviously plays a central role in our study of phase transformations. So we'll talk about kinetics quite a lot. Okay, so let's pretend we have a single component system, right? This is a metal or a molecular liquid how do the thermodynamic variables change with temperature, right? Well, entropy is pretty straightforward, right? We define the entropy at absolute zero to be zero for a pure substance. And then we know that it's going to increase with temperature. It needs to increase monotonically, right? We also know that the specific heat of a pure substance is also going to be zero at absolute zero.
Is this still assuming constant volume? Or does that not matter anymore?
This doesn't matter for right now, right? So we're just saying I've got a pure substance that's not undergoing any phase transformation, and it doesn't have any external confinement on it, right? So we can, it definitely doesn't need to be at constant volume, right? So if you look at the derivation, at the equations here, we're really talking constant pressure for these quick derivations. We could go through a very similar thing for constant volume, and it wouldn't really change much. The actual difference between the constant volume specific heat and the constant pressure specific heats are quite small, right? If you remember the conversion between the two of them from your thermo reading, or maybe you didn't consider that directly, but the difference between the constant pressure and the constant volume case is quite small. The only difference really that it would make would be, instead of enthalpy here, we would have internal energy. But the specific heat at absolute zero tends to zero, right? And which is why absolute zero is essentially an impossible state, right? Because any tiny amount of heat that you put into your system is going to raise a essentially infinitesimal amount of heat is going to have a finite amount on your temperature change as you approach absolute zero, right? So the enthalpy is the integration of our specific heat, right? So we know that if our specific heat approaches zero at absolute zero, the slope of our enthalpy curve has to be zero at absolute zero. So that means essentially this has to come out at a flat line, right? Right? And so thermodynamically, this is how our variables in a single component system look. So what about our Gibbs free energy of a single component, right? Well, we know that the entropy term is zero, right? We have 0 times 0 for Gibbs free energy, right? So that means the initial slope of our Gibbs free energy also has to be 0, right? Because our enthalpy slope is 0. So, so we have that. And then essentially our Gibbs free energy, oops, what did I open? Our Gibbs free energy and our entropy go off in different directions, with the distance between them being our TS term, right? So essentially, these form a mirror of each other, the enthalpy and the Gibbs free energy, about the enthalpy of formation of our single component at 0 Kelvin, right? Okay. What about changes in pressure? Well, we know that the derivative of Gibbs free energy with pressure at constant temperature is our volume, right? And the relationship between pressure and volume is our bulk modulus, which is a measure of our elastic stiffness and bonding strength, right? And so a larger bulk modulus means a larger free energy increment, right? With changes in pressure. So this is really interesting. So what does that mean for things that have our constant volume solids like rubber, right? Natural rubber has a Poisson's ratio of exactly 0.5, which means that when you compress it elastically, it maintains its volume, right? So that means that's essentially what gives us large immediately reversible changes in the stretch, right? Because what this essentially tells us is that any change we make to the internal energy by compressing something has to be immediately balanced by the change in entropy, so that when we compress things, rubber, we're going to have temperature changes. But rubber in and of itself acts like an entropy spring, right? Which is pretty cool, and we can talk about more when you take mechanics of materials, your mechanics class, with either Professor Murphy Leonard. Ariel's going to be teaching that this spring. Okay. So if we have two phases, our temperature and two phases, in this case, a solid and a liquid for our pure substance, right? If we are liquid at high temperature and we cool down, what we see is that our free energy curves will cross essentially at the melting point, right? So at the melting point, at our equilibrium temperature between the two phases, the Gibbs free energy is equal, right? We have an offset, though, in our enthalpy terms, right? So the difference in the enthalpy here means that that this is our latent heat of melting at our equilibrium temperature, right? So that's how much heat our liquid needs to give off at constant pressure in order for the phase transformation to occur, right? As we keep cooling, we now are in a regime where the solid is the lower free energy curve, right? So what's our driving force for the phase transformation? It's this reduction in free energy, right? So at the equilibrium temperature, we have no driving force for the phase transformation, right? It's not going to occur. Well, I mean, if it occurs reversibly. So there's no directionality associated with it because there is no overall reduction in free energy, right? But when we get down here, now there is. Our system can lower the free energy by undergoing a phase transformation. And the difference between these two curves is how much of a driving force there is going to be to overcome the nucleation barrier, or the height of the transition phase, right? Notice if we're to the right of the equilibrium temperature, we have to raise our free energy, right? So it's an impossible process. It is impossible to freeze a liquid above its melting temperature for a given pressure, right? You just can't do it, okay? What about pressure, though? Well, if two phases have different molar volumes, their free energies are not going to increase by the same amount with changes in pressure, right? So equilibrium can be disturbed if we change the pressure. The only way to maintain equilibrium if we vary the pressure is by also varying the temperature, right? And we see that from the Clausius-Clapeyron equation, right? That the change in pressure with temperature, right? We have a change in volume and a change in enthalpy associated with it, right? Generally, an increase in pressure is going to lower the equilibrium transition temperature, right? So we see that with a lot of different substances, right? Is this a review? Well, I mean, a lot of these topics were hit on in thermo, but you may not have seen them presented in exactly this way. So I would say, yes, it is a review. It's still in the material in the slide deck called Critical Thermodynamics Review, but now we're talking about it specifically in the context of phase transformations, right? So it may be presented in a different way than you've seen it before, right? So we see this on the phase diagram, right? So if we increase our pressure, the x-axis on this, right? The phase that has a smaller molar volume essentially acts over a large, is stable over a large region of the phase diagram, okay? So which has a higher enthalpy? Are BCC alpha iron or our FCC gamma iron, right? And it's exactly analogous to the liquid solid, right? The higher temperature phase is going to generally have a higher enthalpy than the lower temperature phase, right? But notice that if we keep a low temperature and we increase our pressure, right, we can also get to a phase transformation, right? In this case, this is epsilon, a HCP phase, right? So it shouldn't really be a strange concept that pressure can also perturb. Okay, so we're almost wrapping this up. I ran a minute and 40 seconds over. I apologize. But we'll finish this off and begin to talk about really new material, the thermodynamics of binary solutions and equilibrium in heterogeneous systems on Friday, right? Then moving forward, we'll talk about phase diagrams, a little detour on polymer solutions. The next major topic is going to be solidification and then solid state diffusion. So we'll see everyone on Friday. Have a good day, and we'll see you then. Okay, thanks everybody. Quick question from Andrew. So would alpha iron or epsilon iron have the higher enthalpy, right? Okay, so if we, I want to make sure I'm not saying something backwards, right? Because my ability to make mistakes is infinite. So it could, I got to think about which way, what's the heat of transformation. In this particular case, the alpha iron, I believe, is going to have a higher enthalpy because the epsilon iron is a HCP, so it's a closer packed and more tightly bonded structure than the BCC. So it should have a give off heat on the transformation. Right? So the system should have to take in heat going from epsilon to alpha. So alpha should have a higher enthalpy, but I will double check that, right? And make sure I'm not saying something backwards, right? Okay, thanks for those of you who stuck on after the time.